Welcome to the webinar on eMTP, ETAP's Electromagnetic Transients Program. eMTP is a new application by ETAP that offers a dedicated EMT program for performing electromagnetic transient simulation and analysis of waveform level phenomenon. ETAP eMTP is an accurate, fast, and mature solution based on the widely used and well-known EMTDC engine powered by PSCAD. Complementing ETAP's analysis modules, eMTP provides simulation of AC power systems, low-voltage power electronics, HVDC, fax, transmission and distribution networks, as well as representation of complex control systems to mitigate network dynamic response concerns. ETAP eMTP runs as a separate application and can be accessed directly from ETAP TS mode. ETAP eMTP is used for a variety of applications, including insulation coordination, switching transients and surges, subsynchronous resonance, ferroresonance, lighting, surges and protection, as well as transient recovery voltage studies. Expanding our offering to provide a multi-domain analysis, ETAP eMTCoSim mode is provided along with eMTP and Transient Stability to offer CoSimulation of electromagnetic and Phasor transients. That is, ETAP's Transient Stability and Electromagnetic Transient programs are combined to collectively solve complex system models with detailed hybrid simulation at millisecond and microsecond time step to analyze the coupling between phasor and electromagnetic domains. eMTCoSim was recently introduced and demonstrated in our webinar. You can watch the recorded webinar by visiting etap.com/webinars. eMTP is a fully featured electromagnetic transient software offered and sold directly by ETAP and packaged for large and small size applications. eMTP Unlimited provides a network license with unlimited nodes. This package is suited for modeling and simulation of larger networks. For smaller systems and at a lower price point, eMTP 200 offers the same features as the unlimited version with restricted EMT network size of 200 nodes. This package is ideal for CoSimulation analysis, and both packages are integrated with ETAP eMTCoSim mode and the functionality for data exchange with ETAP and EMT application. Note that the ETAP bus level is independent from the EMT nodes. Now, let's get a more in-depth insight on EMT analysis and the ETAP EMT applications.
Hello everyone, my name is Darshana Muthumuni and I will be talking about electromagnetic transients, electromagnetic transient simulations to support different design aspects of power systems. During this short presentation, I will provide an overview on electromagnetic transients. I will discuss some common applications and then I will show some actual EMT simulation examples to highlight details and the type of data that you might need and the type of results that you will see from an electromagnetic transient simulation. So we know that when we plan, design and operate power systems or electric networks, you have to do different types of analyses. You have to know how your system would behave in steady state on a day-to-day, hour-to-hour basis. So you have to do load flow studies. Then you have to do transient stability analysis to identify the stability of your system related to generator electromechanical oscillation. Then there are other types of studies, fault analysis, harmonic studies, and finally, for very specific analysis, you have to also perform what we call our electromagnetic transient studies. So let us look at some common applications of electromagnetic transient studies. The so-called fast transients, insulation coordination. Analysis of fast transients for insulation coordination is a very common application of EMT simulations. Some examples are when you switch long transmission lines or cables, that would result in fast, high frequency over voltage transients. Your surge arresters should be able to limit those transients to acceptable levels below your equipment design insulation levels, and also the surge arrestor should be able to absorb the energy associated with the transient. So you perform switching studies to verify your substation design or the arrestor ratings. Similarly, it's common that you perform lightning studies. If lightning hits your conductor, transmission conductor near a substation, what are the resulting over voltages? Can your equipment and your surge arresters handle that over voltage? So this lightning results in very high frequencies and the transients last for a very short duration. So switching lightning are transients that last for nanoseconds or few milliseconds, fast transients. Another common application is the voltage across a circuit breaker when you try to interrupt a current, a fault current or normal load currents. The voltage that appears across the breaker is called transient recovery voltage, and you have to perform electromagnetic transient studies to verify that the transient recovery voltage is within the capability of the breaker. So these are traditional, common, fast transient applications of electromagnetic transient simulations. Now, over the last 5 or 6 years, electromagnetic transient simulations are becoming very important to study the integration of power electronic based devices. Now, with wind and solar and also HVDC becoming more and more common in power systems, the importance of electromagnetic transient simulations have increased. So it is common now to perform EMT type studies to identify the fault right through performance of wind farms, HVDC, and solar farms. When you have two or more power electronic based devices, for example, two wind farms in a local area or a wind farm and a STATCOM fax devices, people have found over the last few years that these devices can interact in a negative manner, unstable manner, and lead to what we call our control interactions. So again, EMT simulations are commonly performed to identify any control interaction related issues. EMT simulations are also used to study harmonics and power quality. Harmonics and power quality for most parts can be analyzed using RMS type programs. However, for example, things like voltage flicker due to an arc furnace. And if you are trying to design a STATCOM controls to mitigate flicker, those type of phenomena cannot be studied easily with RMS type programs, and it's common for engineers to use EMT simulations. Protection modeling, protection and relaying. Once again, you have dedicated RMS type protection and relaying study programs. You don't use EMT programs on a day-to-day basis for protection system studies, but if you want to analyze if certain specific details such as issues with CT saturation, designing of complex controls on a series compensated line, high voltage series compensated line, then it's again common for engineers to verify your design in an EMT type environment. Subsynchronous resonance, the torsional interaction of thermal generator shafts, like interactions that occur at frequencies below 50 Hertz or below 60 Hertz are termed subsynchronous oscillations. Again, those oscillations cannot be studied on RMS and people have to use EMT type programs. So those are some of the common applications, and towards the end of this presentation, I will show some simulation examples to highlight like I said, data requirements, type of results that you can observe through EMT simulations. Next, very briefly, let us look at some of the differences or key differences between RMS type simulations and EMT simulations. The difference can be very easily and simply described using this simple RL circuit. The equation for this RL circuit is V equals Ri plus L di by dt. In EMT programs, we simply write differential equations corresponding to the circuit you want to study and solve it. So we don't, at EMT level, you don't do further simplifications to the fundamental circuit equations. Now, on an RMS platform, when you represent the network, not dynamic devices, generators, even in RMS platform, use differential equations. But the network itself is represented by a phasor equation in RMS programs. For example, in this particular case, the RMS equation for this circuit would be V equals Ri plus J L omega times a phasor I. L omega is your impedance X, and omega is calculated at 60 Hertz or 50 Hertz. Omega is 5 times frequency, 50 or 60 Hertz. So for one, you are limiting your solutions to 50 Hertz. Number two, maybe more importantly, you are ignoring the network dynamics. When you go from the differential equation to a phasor equation, you are ignoring the net dynamics of the electric network, the transmission lines, transformers, and so on. So that really is the main difference between EMT and RMS type programs. The difference is in the way how you represent your electric network. So let us look at some consequences resulting from the two-type equation simplification. Let us look at the consequences of representing the equations using differential equations or with phasor equations. Number one, in an EMT program, when you represent the network with the differential equation, even in steady state, what you would compute are the instantaneous values of voltages and currents. In an EMT program, we don't calculate the RMS value. You calculate the instantaneous value, and then from that, using meters, you can derive the RMS values. So in this particular case, even in steady state, in this case, I have applied a fault, and I'm looking at the recovery of the system after the fault clearance. But even before I apply the fault, in steady state, the instantaneous values are calculated. Then if you look at the recovery of the voltage after the fault, you can see in EMT programs, all the details of the instantaneous voltage are captured. Details such as harmonics embedded in the waveform, they are captured, as you can see. If you look at the waveform that I have shown at the second waveform at the bottom, you can see certain other network dynamics like offsets in voltages and currents following a disturbance are captured in an EMT environment. So in certain situations, these network dynamics may influence the overall response of the system. So that is where you need to perform EMT studies, and that is where RMS studies alone may not give you the full picture. Earlier, I mentioned that EMT studies are becoming more common and probably more important when you are dealing with integrating power electronic interface devices such as wind farms, solar farms, FACTS, or HVDC. There's a very specific reason for that, and I think using one or two slides, I can explain the importance of EMT studies in that situation. Now, EMT studies, EMT simulations, we said, capture the instantaneous waveform. Now, if you have the instantaneous waveform, you can, some measurement or metering technique, you can estimate the angle variation of this voltage. What I mean is, if you say that the zero crossing of a voltage is your reference, then we can say the angle of the voltage will move from 0 to 360 or 0 to 25 in radians. Now, this instantaneous angle measurement, remember, this is not a phase angle that we deal with in phasor simulations. This is the instantaneous angle of the voltage. This angle is a critical input to power electronic controllers. Wind farm or solar inverter controls depends on accurately estimating the angle of the voltage at its connected point to do proper protection and control actions. So what we can say from that discussion is, unlike with synchronous generators, where the inputs to the controllers are RMS measurements or steady measurements such as RMS voltage, power, reactive power, wind farms, solar farms, HVDC also depend on accurately capturing the instantaneous values of voltages to do its job properly. So, and we said that these instantaneous values are only available in an EMT type simulation. Now, this is a good example in my opinion. So when the wind farm is recovering from a fault in this example, you can see that the voltages are not sinusoidal at all. It goes through a transient, there are lots of harmonics involved, there's obviously voltage ramping, the voltage builds up slowly. So from a fault right through perspective, this time frame is also very important. If the wind farm can stay connected during the, let us say, during the first 200 milliseconds following a fault, then most likely it would have successfully rode through this fault. In order for that, it is very, very critical the so-called phase lock loop of the control system of the wind farm accurately captures the voltage angle of the fundamental frequency component of this transient. The most critical measurement that the wind farm controls need to do its job properly or to successfully ride through the fault. If the phase lock loop does not estimate the phase angle or the voltage angle correctly during this transient period, then there's a very good likelihood that the wind farm or the solar farm would fail to stay connected. So if the measurement of this transient is that critical, in RMS programs, you just cannot model these type of transient or represent these type of transients. So this, you can say, is one of the reasons why EMT type programs have become necessary to study the ride-through performance of wind farms and HVDC and solar farms under especially challenging or weak grid conditions. Earlier, I also talked about the other types of network dynamics, the DC offsets in voltages and currents following a disturbance in your grid. We can show that these offsets, the voltage offsets, the current offsets following a fault, also influence the response and the behavior of power electronic based devices. So these offsets are captured in EMT type programs. The harmonics are captured in EMT type programs. All details that can influence power electronic inverter behavior are captured in EMT type programs, and that's one of the reasons why it has become critical or necessary that engineers perform EMT type programs under challenging grid conditions when you try to integrate wind farms or solar farms under challenging grid conditions. Now, there are also situations where the grid conditions are not that challenging, where the so-called short circuit strength at the point of connection is high. The so-called short circuit ratios, the fault level compared to the rating of the wind farm, is high. In those situations, RMS simulations probably would give you the right answer. You don't always have to go into EMT type simulations programs. So that's a little bit of background on EMT type simulations, some common examples, and a little bit of a discussion on why EMT type programs have become more relevant when we are dealing with power electronic inverters or power electronic inverter based devices. Next, I'm going to show you some EMT simulation examples. So we will start with two very common traditional examples: transform energizing and circuit breaker transient recovery voltage related examples. I will directly open my PSCAD and show you the example. I will directly open the EMT simulation program and show you the example. This is a system study model that I developed to study the energizing of this transformer. It's a 75 MVA 66 to 22 kV transformer. So what I have done here is, once the system, my simulation is in a steady state, I have closed this breaker. This red block is a circuit breaker. I have set up the simulation to close the breaker once the system is in steady state. So let me run this, because this case will run quite fast. What I am looking at are two specific things: the RMS voltage at different locations in my system, because transformer, when you energize the transformer, the transformer will absorb a significant current, like called the inrush current, as you can see here. The inrush current can be 5 to 6 or maybe even higher, 5 to 6 times the rated current of the transformer. So when you draw that much current, there is always a possibility that it can cause voltage dips at the bus and also at other customer locations. So you are looking at the voltage dips, and also in this particular examples, the harmonics of the inrush current harmonics of the inrush current can interact with the system and cause what we call a harmonic resonance induced overvoltages. So if I zoom in, the voltage is not sinusoidal following the energization. The voltage is, there are harmonics embedded in this voltage, and sometimes the related overvoltage can be 1.5 or 1.6 times the rated voltage, and that is dangerous. So in a transform energizing study, these are the type of things you would be looking at. Now another example that I can show you is, now I'm assuming that I have two transformers at this location. I have somehow energized the first bank. I'm trying to energize the second bank. And if you look at the results here, and you can see that the inrush has not decayed as fast as in the previous case, and the transformer that was previously successfully energized is experiencing what we called is a sympathetic inrush situation. See? So these are nonlinear events. Obviously, you need to study these in an EMT type environment. Second example that I'm going to show you is related to circuit breaker transient recovery voltage. Once again, I have modeled or represented my system in an EMT environment, but in this case, if I go inside this yellow box, it represents the substation. TRV is a very fast event. Faster the event or higher the frequencies involved, the local elements, the equipment near the breaker influence the transient. Transmission lines, transformers, their response, transmission lines and transformers further from the breaker, like 1 or 2 buses away, have very little impact on very fast transients like TRV. So for a TRV study, what I'm trying to highlight is, in addition to the general system details, you have to also represent the substation in sufficient detail. So once you do that, and when you run the case, what I'm showing you here, the sinusoidal looking waveform, is the voltage that would appear across the breaker poles when you interrupt the current. So in this case, what you are trying to see is if this voltage, the so-called transient recovery voltage, we are trying to see if it is within the capability of the breaker. These line segments I have drawn correspond to the capability of the breaker. We don't want to go into details, but what you have to ensure is that the actual voltage is within the corresponding or the relevant line segment or the TRV capability envelope. So those are two very common traditional type EMT study examples. Next, I will show you an example on renewable integration, wind farm fault response example. In this example, I will show that if you try to inject too much wind power into that particular point in the grid, the wind farm will not ride through certain types of faults. In those situations, again, you use EMT type programs to find solutions, mitigation measures. First, you would try to modify the controls of the wind farm to see if it can solve your problem, because that is the cheapest solution. If that is not possible, then you would look at other mitigation, more expensive mitigation measures, such as adding STATCOMs or other fax devices or synchronous condensers. And in those situations, what you want to know as an engineer is, what is the minimum rating of a synchronous condenser or a STATCOM that I can get away with and solve this problem, because the rating of the STATCOM will determine the cost of your solution. So I will show you a number of examples related to a wind farm study. One thing also to keep in mind that I mentioned before, when you have 2 or more power electronic based devices or fast reactive power control devices in a weak local area, those two or more devices can interact in an unstable manner, and following a disturbance rather than settling into a steady stable state could go into this state called unstable interaction state, where you will have poorly damped oscillations or even sometimes unstable oscillations. These are also studied using EMT type programs. So next I will go to a PSCAD case and show you some examples. This is a simple example to highlight certain points. So what I have done here is I have connected a wind farm, a wind turbine model to this point of connection, POC. In an EMT program, when you study wind and solar, what you commonly do is you model a single turbine unit, a single module in detail, and then aggregate it to represent the entire wind farm. In this particular case, I'm assuming that my wind turbine is rated at 5 megawatts. So I don't know if you can see this clearly. I have aggregated it to represent 25 turbines operating in a wind farm. So the total rating that I'm trying to inject to this point of connection is about 125 megawatts. And then on this simulation, what I'm trying to see is if there is a fault on a line close to the point of connection, and if I clear that fault by opening the breakers within the standard or normal breaker clearing, fault clearing times, can this wind farm and the system survive and ride through the fault? My simulation, the results that you see here show that this wind farm will not ride through the fault. So I'm not going to run this case again. What I'm going to do is, now I have an issue. I have to find a mitigation option. So after trying to modify controls to overcome the issue, if that fails, I have to see if I can mitigate the fault right through issue with a STATCOM or a sync condenser or something similar. So in this case, what I'm going to do now is I'm going to enable or add a sync condenser to the bus. So I'm starting with a 40 MVA sync condenser, and see if a 40 MVA sync condenser with typical parameters and controls can mitigate the issue. If it does mitigate this problem, then I will see if I can lower the rating of the sync condenser to maybe 20, 15, because the idea of the study is to find the cheapest solution. So let us see what the response is after I connected the sync condenser. Yeah, the fault comes on at 5 seconds, and you can see, unlike in the previous case where the voltages were oscillating and eventually the wind farm would trip, in this case the response is stable. Whether the response is acceptable or not is a different question. If the oscillations, the recovery times are not acceptable or are not meeting your grid code, then you have to further refine the controls of the sync condenser and the wind farm. But this was a simple illustration to show you how we go about performing EMT type studies to facilitate integration of wind and power electronic based devices. Now if I go inside this wind farm, wind turbine model, at an EMT level, the model represents pretty much all the details of the real design. The generator type, like in this case, I have used a permanent magnet generator model. If I go inside this page, the power electronic inverters are represented in switching level detail. Important features of components of a inverter, specifically the DC link, the chopper at the DC link is always represented in EMT type simulations. And then if you go to the controls of the power electronics, once again, controls, protection functions, limiting functions, ramping functions are all modeled in detail, closely resembling the actual design. Of course, in this example, I am using a generic model of a wind turbine. When you do more specific studies, the model of the wind turbine would come from the equipment supplier. I have another example where I tried to see if certain oscillations or undervoltage issues could be mitigated using a StatCom. So in this case, I have copied a standard generic StatCom model and connected it to this bus 1, that connected it to what I call is bus 1. Bus 1 is very close to this wind farm. And in this example, I have sized and tuned the controls to mitigate an undervoltage issue that I was seeing without the before I installed the StatCom. Again, because of the time, we don't want to go into details of the StatCom controls and design. I just wanted to highlight what are the possibilities with EMT type programs. Finally, I will show you 2 other examples. One is a generic example of a solar farm. Sometimes when you try to perform studies, you don't always get the specific model from the vendor. So in these cases, it is not ideal, but when you don't have any other option, it is common to use a generic model, a validated generic model, and modify some of the controls, ramp rates, protection settings, and so on to reflect the grid code of that particular country or the region. So these are all possible. So you can see in this example, I have shown the power plant controller and the solar farm as 2 separate modules. Power plant controller provides the references to the solar farm. And if I go inside the solar farm module, just like I showed you with the wind farm, you can see the details of the power electronic inverter, the DC link, the filters, and then also the controls. Finally, I will show you an example of an HVDC system. I'm going to show you a very standard example of the so-called C-Gray HVDC benchmark. And for most generic type studies, most studies that engineers would do, we would use a generic model, generic example, and change the ratings and basic parameters to reflect our specific installation or the device. And then connect this to your system model and try to see at a high level or the preliminary design level what might be the concerns that you will have to overcome in order to add these type of devices. So in this particular example, you will see again the inverters, the rectifiers, the filters, and the control systems of this HVDC model. Once again, given the time that we have, we can't go into details. I just wanted to highlight and show you what is available, what are the possibilities when you go into electromagnetic transient type simulations. Now, moving on to a different but related topic. Now, in EMT programs, we calculate the instantaneous value. The computational burden is much higher than if we were to do similar type of studies in an RMS program. So in EMT type programs, it is not that common to represent very large AC network models in a simulation. Most of the time, if you are studying the response of a wind farm, or if you are studying transformer inertia or breaker TRV, the system would be represented up to 2-3 buses from the point of connection, and the rest would be modeled, represented by equivalent Thevenin voltage sources. So that's the traditional approach of EMT simulations. But with co-simulation possibilities, we have the possibility to represent a smaller part of the system in detail in an EMT program, and then the larger network in an RMS type program to gain benefits from the advantages or the strengths of EMT as well as RMS type programs. So we will demonstrate this possibility to you next. But before I hand over the presentation to my colleague, I will discuss the example or the concept of this co-simulation. The example we will show will be very similar to this in concept. What we will do is we will model the network in an RMS platform. This network would be in an RMS platform. The details of the wind farm, the controls, protection would be in the EMT platform. And they would communicate between the two simulation platforms and perform what we call is a co-simulation or a hybrid simulation. So with that, I will hand over the presentation to my colleagues who will demonstrate this co-simulation.
We will now demonstrate the co-simulation between ETAP Transient Stability and eMTP Electromagnetic Transient Program. ETAP TS Mode toolbar provides the means to perform transient stability and EMT analysis using the eMTP software, as well as performing co-simulation studies between the phasor and electromagnetic domains. In ETAP 20, eMTCoSim analysis is provided for a single boundary block representing ETAP equivalent network at the CoSim element boundary bus. The wind farm is modeled in this subsystem as a lump load. The dynamic model in eMTP domain is used for the co-simulation. The event applied to the phasor domain can be seen in the Event tab in the study case editor, where in this case, a 3-phase fault is applied to the wind farm at 5 seconds and cleared after 100 milliseconds. To initiate the co-simulation, we launch the associated EMT project in the eMTP application. Type 4 wind generators with high fidelity models are used in this wind farm. We can see that the 20 WTG units are modeled in the network, and the blue block represents the dynamic model of the entire phasor network. Let's run the transient stability simulation with the eMTCoSim mode enabled to start the co-simulation. Both phasor and EMT analysis engines are now running in parallel. The phasors and EMT waveforms can be observed during and after the co-simulation. The effect of the event on the phasor network can be seen in the EMT network. In this case, due to the fault on the bus close to the wind farm, the WTG voltages reduce significantly. However, as they are equipped with the controls, they can ride through the fault. At the end of the simulation, eMTCoSim generates the plots for boundary bus, including phasor and EMT data. Results can be plotted using ETAP's live plots and displayed on the views. We hope you enjoyed our webinar and gained a deeper understanding of EMT modeling, simulation, and applications using ETAP eMTP based on a trusted EMT simulation engine. You can learn more about eMTP by visiting etap.com/eMTP.